Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll explore the core concepts that define Elastic Cloud Compute, or EC2, from how virtual servers are provisioned and managed, to the underlying architecture that enables scalability, high availability, and elasticity. We'll break down the different instance types and families, the concept of instance lifecycles, and the role of AMIs. We will also touch upon the concept of security groups. Let's get started. Amazon EC2, or Elastic Compute Cloud, is one of the most fundamental building blocks in the AWS Services Catalog. It was designed with a clear goal: to make web-scale cloud computing easier and more accessible. At its core, EC2 provides resizable compute capacity in the cloud, giving users a true virtual computing environment where they have full control over their infrastructure. Whether you're running a small application or a large-scale enterprise workload, EC2 lets you scale compute resources to match your needs. To support a wide range of use cases, EC2 offers various instance families optimized for different workload profiles, from general purpose and compute-intensive to memory-optimized and accelerated computing. You can launch these instances from pre-configured Amazon Machine Images, or AMIs, which provide a consistent, version-controlled environment, or you can create your own custom AMIs to meet your specific requirements. And when it comes to scaling, EC2 is designed for flexibility. Instances can be scaled manually as your needs evolve, or automatically through auto-scaling, helping ensure high availability and performance while optimizing costs. Here is a screenshot of the official blog post from Jeff Barr, the chief evangelist at AWS, marking the historic beta launch of Amazon EC2, Elastic Compute Cloud. This was a pivotal moment in the evolution of cloud computing, as EC2 introduced the revolutionary idea of on-demand, scalable virtual servers in the cloud. What began as a simple beta service has since grown into one of the most foundational and widely used services in the AWS ecosystem, powering everything from startups to global enterprises. This post reflects AWS's early vision for cloud computing: flexible, self-service infrastructure at massive scale, a vision that has shaped the industry ever since. Amazon EC2 is one of the most widely used services in the AWS ecosystem, and for good reason. It offers powerful, flexible capabilities that make it a go-to solution for running virtually any kind of workload in the cloud. With EC2, you can rent virtual machines equipped with compute power and memory tailored to your application's requirements. You also have access to scalable storage options, such as Elastic Block Store (EBS) for persistent volumes and Elastic File System (EFS) for shared file storage. To ensure your applications remain responsive under load, EC2 integrates with Elastic Load Balancing (ELB), which automatically distributes traffic across multiple instances. And with auto-scaling groups, your infrastructure can automatically scale up or down based on demand, helping you maintain performance while optimizing costs. Each EC2 instance operates within an Amazon Virtual Private Cloud (VPC), giving you granular control over networking, IP addressing, routing, and security, including security groups and network ACLs. You can launch instances with a wide selection of operating systems, from common Linux distributions to Windows Server, and run as many or as few systems as you need, scaling to meet your business or development goals with ease. There are two concepts that are key to launching instances on AWS: the amount of virtual hardware dedicated to the instance, and the software loaded on the instance. The instance type defines the virtual hardware supporting an Amazon EC2 instance. When configuring an EC2 instance, there are several key components to consider, each of which directly impacts the performance, cost, and behavior of your compute environment. First, you'll choose an instance type, which determines the virtual machine's hardware configuration, including the number of virtual CPUs, the amount of RAM, and the type of operating system you want to run. AWS offers a wide range of instance families to suit different use cases, from general-purpose workloads to compute or memory-intensive applications. Next is storage. EC2 provides two primary storage options: the Instance Store, which offers high-speed ephemeral storage physically attached to the host machine, and network-attached storage such as EBS for persistent block-level volumes, or EFS for shared scalable file storage across multiple instances. Finally, networking, which is another critical element. When launching an instance, you configure its network performance, assign private or public IP addresses, and define how it communicates within your Amazon VPC. To protect your instance, you use security groups, virtual firewalls that control inbound and outbound traffic based on defined rules. All of these configuration choices, from compute and memory to storage, networking, and security, work together to ensure your EC2 instance is tailored to your application's specific needs. Choosing the right instance type is all about striking the right balance between performance and cost. You want an instance that provides just enough resources to meet your application's requirements without over-provisioning, which can lead to unnecessary expenses. As your workload evolves, perhaps due to increased traffic, new features, or changing performance requirements, EC2 offers the flexibility to resize your instance. You can simply stop the instance, change the instance type, and start it again, scaling your compute resources up or down as needed without re-architecting your application. This flexibility is one of EC2's key strengths, making it easy to adapt your infrastructure to your business and technical needs in real time. EC2 instance types follow a standardized naming convention that helps users quickly identify key characteristics of the instance at a glance. This naming system provides insight into the instance's generation, class, processor type, and size, which is especially useful for selecting the right instance for your workload and understanding its capabilities without having to look up the full specs each time. For example, take an instance named m8g.xlarge. Let's break down what this name means. M, this is the instance family, or class. In this case, M stands for General Purpose Instances. 8, this indicates the generation of the instance. Newer generations generally offer better price-performance ratio. G, this suffix identifies the processor architecture. In this example, G stands for Graviton, which means this instance runs on the in-house AWS Graviton processors. X-large, this denotes the instance size, which directly corresponds to the number of vCPUs, virtual CPUs, and RAM memory allocated. This naming convention is consistent across all EC2 instances, allowing for easier identification. As the name implies, general-purpose instances are designed to provide a balanced mix of compute, memory, and networking resources. This makes them ideal for a wide range of everyday workloads where no single resource dominates. Typical use cases include web servers, application servers, development and test environments, and code repositories, where consistent, moderate performance across all resource dimensions is more valuable than specialized performance in one area. Within this category, the T-class instances, like T3 and T4G, are known as burstable performance instances. These are especially cost-effective for workloads with variable CPU usage. During periods of low activity, the instance consumes fewer CPU cycles and accumulates CPU credits. When your workload demands spike, these credits are used to temporarily boost CPU performance, enabling the instance to burst beyond its baseline level. This burstable model allows you to run lightweight or intermittently demanding applications at a lower cost, while still maintaining the ability to handle occasional performance surges without upgrading to a larger, more expensive instance type. It's a great choice for predictable workloads with occasional peaks, such as microservices, small databases, or internal tools, offering both flexibility and cost efficiency. Compute-optimized instances are purpose-built for workloads that require high-performance processing power. These instances feature a high ratio of vCPUs to memory and leverage the latest generation of high-frequency CPUs to deliver consistently fast performance for compute-heavy tasks. They are particularly well suited for scenarios where the primary bottleneck is CPU throughput, rather than memory or I/O. Common use cases include batch processing jobs, video encoding and media transcoding, high-performance web servers, scientific and financial modeling, dedicated game servers, ad tech engines, and machine learning inference, where low latency and deterministic performance are critical. By isolating compute as the primary resource, these instances provide a cost-effective solution for high-demand environments where raw processing speed is paramount. On the other end of the spectrum, bare metal instances provide direct access to the physical hardware, bypassing the virtualization layer. These instances expose the underlying CPU, memory, and I/O devices to your operating system, offering maximum control and performance. Bare metal is ideal for specialized workloads that require low-level hardware access, such as high-performance databases, real-time data analytics platforms, or custom hypervisors. They're also a strong fit for legacy applications that can't operate in a virtualized environment, or for software with licensing restrictions that limit the use of virtual machines. Memory-optimized instances are engineered for workloads that require high memory capacity and bandwidth, delivering fast and efficient performance when processing large datasets in memory. These instances provide a higher ratio of memory to vCPUs compared to general-purpose or compute-optimized types, making them ideal for memory-intensive applications where performance is directly tied to how much data can be stored and accessed in RAM. Typical use cases include open-source databases like MySQL, PostgreSQL, and MariaDB, in-memory caches such as Redis and Memcached, and real-time big data analytics platforms like Apache Spark or Presto. These workloads benefit from rapid data access and minimal I/O latency, which memory-optimized instances are specifically designed to provide. For enterprise-scale, mission-critical applications, AWS offers a specialized subclass, the EC2 high-memory U1 instances. These are purpose-built for running extremely large in-memory databases, such as SAP HANA, in a cloud-native environment. U1 instances support terabytes of RAM, enabling customers to migrate or deploy production-grade HANA workloads without sacrificing performance or control. These instances are fully integrated with the AWS ecosystem, offering the elasticity and scalability of the cloud while meeting the stringent performance and reliability requirements of enterprise data platforms. This makes them an ideal solution for organizations modernizing their ERP systems, analytics platforms, or large-scale transactional databases. Storage-optimized instances are purpose-built for applications that require high throughput and low latency access to large volumes of data stored locally. These instances are ideal when your workload demands intensive, high-speed read-write operations, particularly for sequential and random I/O access patterns. They leverage locally attached NVMe SSDs to deliver extremely fast and consistent performance, with the ability to handle tens of thousands of IOPS and high disk throughput, making them particularly well-suited for workloads like NoSQL databases, e.g. Cassandra, MongoDB, distributed file systems, data warehousing, log processing, real-time streaming data applications, and high-performance analytics. These instances shine in scenarios where latency and IOPS are critical bottlenecks, and where data locality, having the data physically close to the compute, is key to achieving the required performance. AWS offers storage-optimized instances in families such as the I-series, e.g., i3, i4i, and D-series, each tailored for different performance needs. Many of these instances support NVMe storage with direct access, enabling minimal overhead and near bare metal disk I/O performance. Accelerated computing instances are specialized EC2 instance types that leverage hardware accelerators, such as GPUs, graphics processing units, FPGAs, field programmable gate arrays, or custom AWS-designed chips, to offload and accelerate compute-intensive operations that would otherwise be inefficient or slow on standard CPUs. These hardware coprocessors are ideal for tasks that involve floating-point arithmetic, matrix operations, graphics rendering, or pattern recognition. This makes accelerated computing instances an excellent choice for workloads like machine learning training and inference, 3D rendering, video transcoding, genomics, and real-time analytics. By offloading complex parallel computations to dedicated accelerators, these instances not only deliver significant performance improvements, but also improve cost efficiency by reducing overall execution time. Complementing this are the high-performance computing (HPC) instances, which are purpose-built to support large-scale, tightly coupled workloads that demand maximum computational throughput, low latency networking, and high memory bandwidth. These HPC instances often include custom-built, high-frequency CPUs, enhanced networking with Elastic Fabric Adapter (EFA) for low-latency internode communication, and optimize storage configurations to support compute-heavy simulations. Use cases include fluid dynamics, finite element analysis, seismic modeling, weather forecasting, and deep learning at scale, where traditional cloud infrastructure may not offer the performance or interconnect required. Together, accelerated computing and HPC instances bring the power of specialized high-performance hardware to the elasticity of the cloud, enabling organizations to run the most demanding scientific, engineering, and AI workloads efficiently and at scale on AWS. When you launch an EC2 instance, the Amazon Machine Image, or AMI, acts as the blueprint that defines the initial software state of that instance. It includes everything needed to boot and run the system: the operating system, any pre-installed applications or libraries, the initial configuration, and any patches applied at the time the AMI was created. Essentially, the AMI determines what software environment your instance will start with, whether it's a bare operating system or a fully configured application stack. There are three primary sources of AMIs: AWS published AMIs. These are official AMIs maintained by AWS that offer standard versions of popular operating systems, such as Ubuntu, Red Hat, SUSE, Windows Server, and Amazon Linux. These images are ideal if you want a clean OS install, much like starting from an official ISO. AWS Marketplace AMIs. The AWS Marketplace is a curated catalog of software offerings provided by third-party vendors. Here, you can find pre-configured AMIs bundled with commercial or open-source software, like databases, security tools, and enterprise applications. These images often come with additional licensing costs, so when you launch an instance from one of these, you're charged not only for the EC2 instance, but also for the software license. Private or custom AMIs. You can also create your own AMIs based on a running EC2 instance. This is extremely useful when you've configured an instance with your specific software stack, patches, and settings, and you want to replicate it across your environment. AMIs can also be imported from external virtualization environments using the VM import-export service. However, it's your responsibility to ensure compliance with any licensing terms associated with your operating system or software. By leveraging different types of AMIs, you gain flexibility and control over the deployment and scaling of your EC2 instances, allowing you to automate, replicate, and maintain consistency across your cloud infrastructure. Creating custom AMIs is a powerful way to gain control, consistency, and efficiency in your EC2 deployments. By capturing a pre-configured image of an EC2 instance, you can standardize environments, streamline operations, and support advanced use cases like rapid provisioning, security hardening, and disaster recovery. Custom AMIs allow you to build golden images, base templates that include your preferred operating system, software stack, configuration settings, and security controls. This ensures every instance launched from the image is identical, making deployment predictable and reproducible. Whether you're deploying web applications, microservices, or background jobs, packaging everything into an AMI eliminates environment drift and reduces deployment errors. They're also ideal for testing and development environments, enabling developers to replicate production setups for better debugging and QA. By pre-installing the necessary software and optimizing configurations, your instances can boot faster and perform more efficiently. This is especially useful in auto-scaling scenarios where fast provisioning of instances is crucial. Tailoring the OS and performance settings within the AMI ensures your workload is finely tuned for its needs, right from the start. Custom images let you bake in exactly what you need, whether it's enterprise software, language runtimes, or embed custom security policies and hardening steps to ensure a secure, compliant baseline for every instance. Here's a quick look at how to create a custom AMI. Start with an existing AMI and launch an instance from that AMI. Customize the instance by installing your software, configure settings, remove temporary files, etc. Create an image from that configured instance. Launch new EC2 instances from the resulting AMI as needed. EC2 Image Builder is a fully managed AWS service designed to simplify and automate the creation, management, and deployment of customized, secure, and up-to-date server images. With EC2 Image Builder, you retain full ownership of the images created within your AWS account. You can define image pipelines that automate everything from regular software updates and patching to testing and deployment. Alternatively, you can trigger builds manually for greater control. One of the biggest advantages of Image Builder is the increase in productivity and operational efficiency. By defining build pipelines with scheduling preferences, AWS automates the entire image creation process. This significantly reduces the time and effort required to maintain up-to-date and compliant server images. Image Builder also plays a crucial role in enhancing uptime and reliability. Built-in testing components ensure that images are verified before being distributed. Only images that pass all defined tests are made available for use. On the security front, Image Builder lets you create hardened images that adhere to best practices and industry standards. You can apply predefined AWS security settings or build your own configurations to reduce exposure to known vulnerabilities. Finally, sharing your resources across AWS accounts is straightforward with support for AWS Resource Access Manager, RAM, and allows you to easily distribute approved images across your organization. While at first glance, custom AMIs and EC2 Image Builder may seem similar, it's important to recognize the key differences. Custom AMIs are manually created, one-off images tailored for specific configurations, making them ideal for quick or small-scale use. They require manual intervention for each update or customization. In contrast, EC2 Image Builder automates the entire process of image creation, testing, and compliance at scale. This service ensures consistent, secure, and repeatable deployments, eliminating the manual effort and providing a more efficient solution for large environments and enterprises that require ongoing updates and governance. Amazon EC2 provides broad support for various operating systems, OS, giving you the flexibility to choose the one that best fits your application requirements. EC2 instances can run popular Linux distributions, including Amazon Linux, Ubuntu, Red Hat, CentOS, and SUSE Linux, as well as Windows Server versions, including Windows Server 2016, 2019, and 2022. In addition to the mainstream OS options, EC2 allows you to bring your own custom operating systems or specialized versions using custom AMIs. This flexibility is ideal for businesses that have legacy systems or specific OS requirements. By supporting a wide array of operating systems, EC2 allows you to seamlessly run applications, whether you're using open source software, enterprise applications, or proprietary systems, ensuring compatibility and performance for virtually any workload. In AWS, security groups act as virtual firewalls that control the traffic flowing into and out of your instances. These firewalls are designed to filter network traffic based on three key attributes: port, protocol, and source destination. When launching an EC2 instance, you associate it with one or more security groups. Every instance must have at least one security group, but it can be associated with multiple groups if needed. By default, security groups are set to deny all traffic, and only traffic explicitly allowed through security group rules is permitted. Each rule in a security group is defined by three main attributes. Port specifies the port number affected by the rule, e.g. port 80 for HTTP. Protocol defines the protocol for communication, such as TCP for HTTP traffic. Source destination refers to the communication endpoints, where the source is for incoming traffic and the destination is for outgoing traffic. If an instance is associated with multiple security groups, their rules are aggregated, allowing all traffic permitted by any of the groups. This provides flexibility in defining and managing network security at the instance level. Here is an example of how the security group will function. On the inbound side, imagine you've set up a rule to allow only SSH, port 22 traffic from a specific IP address, say 192.168.1100. This means that only traffic originating from this IP address will be allowed to connect to your EC2 instance on port 22, which is commonly used for secure shell SSH connections. If any other IP address attempts to establish an SSH connection, whether it's from an external network or another instance, the connection request will be denied. This gives you precise control over who can access your instance. On the outbound side, the security group could be configured to allow all traffic without restrictions. This means that the instance can initiate connections to any external destination without any firewall interference. For example, your EC2 instance could access external services, databases, or APIs on any port, with no constraints on the destination. This flexibility allows you to configure your security groups based on the needs of your application, ensuring that you can both control access to your instances and facilitate necessary communication with external services. When configuring security groups or network access for your EC2 instances, it's important to be aware of the classic ports commonly used for various protocols. Here's a quick reference to some of the most frequently encountered ports. Port 21, FTP, used for File Transfer Protocol, FTP, which allows the transfer of files between a client and server, typically used in scenarios where file uploads or downloads are required. Port 22, SSH, Secure Shell, SSH, is used to securely access and manage instances over the network. It's essential for logging into Linux-based instances and remotely administering them. Port 80, HTTP, the standard port for Hypertext Transfer Protocol, HTTP, which is the foundation of data communication on the web. It's commonly used for unencrypted website traffic. Port 4443, HTTPS, the secure version of HTTP, HTTPS, Hypertext Transfer Protocol Secure, operates over port 443. It ensures encrypted communication between a client and server, commonly used for secure web traffic, such as online banking or e-commerce sites. Ports 161, 162, SNMP, Simple Network Management Protocol, SNMP operates over ports 161 for queries and 162 for traps. These are used for managing and monitoring devices in a network. Port 3389, RDP, Remote Desktop Protocol, RDP, is used for accessing and managing Windows-based EC2 instances. It allows remote access to the graphical interface of a Windows server, making it critical for administrators working with Windows instances. Being aware of these ports is essential when configuring security groups or ensuring secure access to your instances. Security groups in AWS live outside the EC2 instance, meaning they act as virtual firewalls that control traffic to and from the instance, rather than being embedded within the instance itself. This setup allows a security group to be attached to multiple EC2 instances, ensuring consistent security policies across them. By default, security groups are configured to authorize all outbound traffic, allowing instances to initiate connections to external resources without restrictions. Block all inbound traffic, denying any incoming connections unless explicitly allowed through security group rules. When troubleshooting issues related to accessibility or connectivity, it's important to differentiate between the causes. If an application is not accessible, the problem is typically related to the security group configuration, which is blocking inbound traffic. If an application returns a connection refused message, the issue is usually an application error rather than a network or security group issue. Understanding how security groups function and their default settings is crucial for diagnosing and resolving connectivity problems effectively. When you launch an Amazon EC2 instance, you have the ability to pass user data that can be used to automate configuration tasks or run scripts automatically after the instance starts. This capability allows you to pre-configure your instance at launch without having to manually log in and make the changes yourself. For Linux instances, there are two main ways to pass user data. First, shell scripts. If you're familiar with shell scripting, this is often the easiest and most flexible way to send configuration instructions to an instance at launch. These scripts can automate complex tasks, saving you time and effort. However, it's important to remember that adding tasks to run at boot time will increase the time it takes for your instance to start up. Therefore, it's recommended to allow a few extra minutes for these tasks to complete before testing that everything has been configured successfully. Second, Cloud Init directives. The Cloud Init package is another powerful tool used for configuring new instances, particularly Amazon Linux instances. This package allows the instance to be pre-configured with tasks, like setting up the authorized keys file for the default EC2 user, allowing secure SSH access with your own private key. You can pass Cloud Init directives at launch, just as you would a shell script, though the syntax differs. Cloud Init provides a way to manage instance configuration that is more structured and adaptable than shell scripting alone. By leveraging user data, whether through shell scripts or Cloud Init directives, you can automate the initial setup of your EC2 instances, ensuring a consistent, repeatable deployment process every time. Adding these tasks at boot time adds to the amount of time it takes to boot the instance, so it's important to allow some extra time for the instance to fully initialize and complete the configurations before testing. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.